Greetings, Professor. Can you hear me?
Oh, yes.
Nice to see. Nice to meet you. Yeah.
Okay, so it's already, maybe we can start. So good morning, everyone. Today, we are happy to invite Dr. Joo Hwan Oh to
Yeah.
give us an invention lecture. First, I will introduce him briefly. So Dr. Oh is an associate professor in the Department of Mechanical Engineering in Ulsan National Institute of Science and Technology, where he has been since 2016. His main research interests span vibration, elastic waves, and elastic metal materials. Much of his work has been on developing new elastic metal materials and wave devices based on them. During his career, he has published various remarkable papers, such as the recent one selected as the editor's pick in Applied Physics Letters. Currently, he is focusing on the low-frequency elastic metal materials, elastic metasurface, and nonlinear elastic waves. So today, his presentation title is Elastic Metasurface for Wave Mode Tailoring. Okay, now welcome, please.
Okay. Thanks for a very nice introduction. Let me share my presentation first. Okay. So can you see my presentation?
Oh, yes.
Okay. Thank you. So, greetings, everyone. My name is Joo Hwan Oh from Ulsan National Institute of Science and Technology, which we call UNIST in South Korea. And first, before my presentation, it's my great honor and pleasure to have the presentation with you. And I'd like to thank for Professor Yang-Feng Wang about providing this very honorable chance to me. So, uh, today I will talk about the elastic metasurfaces for wave mode tailoring, especially focusing on the elastic metasurfaces to tune the wave mode from the longitudinal to shear waves. So before the presentation, let me just introduce my university. So you know this. I think all of you know about the South Korea is very close to China, and in South Korea, at the southern part of the South Korea, there is a city called Ulsan. So over here, yeah. So my university is located here, which is located a little bit far from Seoul. It takes 2 hours from Seoul by high-speed train. But anyway, my university is founded in the year of 2007 and opened in the year of 2009, which means that it is very, very young university. So it's now almost around 15 years old or something like that. It's like a teenager in the university. So it's very young university. But anyway, our university is really focusing on the researches. So it has a very high ranking among the global universities. So let me introduce the idea of the metasurface, which is the main research topic and main idea of my presentation. I'm not sure whether all of you are familiar with the idea of metamaterial, but the metamaterial is the artificially structured composites materials of array of units, which means that the metamaterial is an artificial material consisting of a sub-wavelength unit cells. In the metamaterial, by using the idea of metamaterial, by using the internal dynamic phenomena like resonance or periodicity or scatterings or something like that, by using the idea of wave physics of the unit cell, we can achieve very interesting extraordinary wave characteristics such as negative densities, negative stiffness, or something like that by using the idea of metamaterial. And metasurface is a surface version of the metamaterial. So here is the typical metasurfaces which has been published previously. And here the metasurface is the artificial surface consisting of the unicells. So here if you see if you focus on this research, you can see that we have very thin artificial surface consisting of this kind of unicell structures. And if we put this kind of unicells and arrange the unicell to make the artificial surface, and then as you can see here inside the unicell, it has own configuration, which means that it can have a resonance at a certain frequency, and sometimes it can have a scattering, or sometimes it can have some other wave physics at a certain frequency. And by combining those kind of physics, we can tailor the wave propagation, and we can change a lot of things by using very thin surface. And that is the idea of metasurface. So here, this one is not carried out by my research group, but this one was carried by my previous PhD advisor's research group. And here the main goal is to refract the wave propagating along this direction. So if the wave propagates along the normal direction, then it should propagate along the normal direction, even if it face any kind of surface or any kind of boundary. But by using the idea of metasurface, we can change the wave's propagating direction by using very thin surface. And that is the main idea of the metasurface. So let me just introduce Let me just introduce the basic principle of the metasurface. So this one is the acoustic metasurface, which was proposed by Professor Kumar's group, which is in the Duke University, which is one of the leading group in the field of acoustic metasurface. So here, their idea is to introduce this kind of artificial surface, and they place this artificial surface here. And if this artificial surface is placed, even if the wave instant along the normal direction, it will be refracted along this direction, which is impossible by using the conventional surface or wave physics. But by using the idea of metasurface, we can achieve this kind of thing. So to figure out the operating principle of the metasurface, let's call each of unicell as unicell 1, 2, 3, 4, 5, 6, 7, 8, or something like that. So here, you can see that each unicell has its own configurations like this. And here, each unicell is designed to provide a certain phase shift like this. Certain phase shift at a given frequency. So for example, in the unicell number 1, the unicell number 1 is designed such as if the acoustic wave is instant along this direction, it will be totally transmitted without almost no reflection, but with a certain value of phase shift like this. And the unicell number 2 is designed to have almost 100% transmission and with some different phase shift compared to the unicell number 1. So you can see the phase difference you can see a clear phase difference like this one and this one. You can see the phase difference, okay, like this. And they also designed the unicell number 3, unicell number 4, unicell number 5 to unicell number 8 to introduce a certain value of phase shift like this. So if the acoustic wave normally instant's to each unicell, then the transmitted wave will have a certain value of phase, and it will provide a phase shift for each unicells. And if you combine all of these waves into the metasurface to form a single surface, then obviously the wave which is transmitted through the surface will propagate along this direction. because of the phase shift. And by adopting the proper value of phase shift, we can tune the waves propagating direction. We can refract the waves propagating direction. So the main idea of metasurface like this, we should introduce the artificial unicells that provide 100% transmission and a proper value of the phase shift. So by using the metasurface, there has been a lot of researches previously. So especially if we just focus on the elasticity, then there has been some researches like I've introduced you in the previous slide like this. Okay, so by using the idea of metasurface, we can tailor the waves propagating direction as we desired by using very thin surface, which means that we can have very small wave device. While if we use the idea of materials, then we should have very large sized materials. But however, previously, even though its name was metasurface, the actual thickness of the surface was not very thin. So as you can see here, the metasurface consists of 4 unicells along the waves propagating direction like this. And even in the previous case, in acoustic metasurface, they used 4 unicells along the propagating directions, which means that even though its name was metasurface, it was actually not a surface. It was not very thin enough. So what I tried during my research is to introduce really thin metasurface consisting of only a single unit cell. And that is the main topic of our this presentation and this lecture. So in this lecture, I'd like to show you the idea of metasurface, which means that the idea of making the artificial unicells to tailor the waves propagating direction within very thin artificial surface, within a single unit cells along the propagating direction. So if we can do that, we can have very thin and very small sized ultrasonic acoustic devices, which should be very good for various applications like non-destructive evaluations or medical ultrasonic imaging applications or etc. Okay, so that is my main research topic. And today, especially, I'd like to focus on the wave mode conversion, which is one of the unique phenomena appearing in the elastic waves only. Okay, so let me start from how we can design the single unit metasurface. How can we design the unicells to provide 100% full transmission and a proper phase shift? Okay, so if we can achieve these two requirements, if we can achieve full transmission, and if we can achieve any desired phase shift values, then we can have the elastic metasurface. We can have very thin artificial surface that can tailor the waves propagating direction through any directions. Okay, so this would be the basic building block of the metasurface. So to this end, we just introduced this kind of very simple mass spring system. So this one is the equivalent mass spring system we first studied to figure out the required conditions for the metasurface unicell design. So based on this kind of very simple mass spring system, we derived the transfer matrix, and based on that transfer matrix, we could calculate the transmission coefficient like this. So here T11, T21, T12, all of these variables are given like this. So these obviously all of these values are a function of the effective spring coefficient and mass coefficient here. So as you can see here, the transmission value is given like this. And this transmission value is obviously complex value, which means that if the waves propagate through this metasurface, then it should have a proper phase shift. That is the reason that the transmission coefficient becomes complex value. Okay, so we derived all of those things, and based on that, we can have the phase shift, as I told you previously, and we figured out the required conditions to achieve the desired phase shift values. So for like this, so here is the main idea. Okay, so as I told you, the transmission coefficient for this given equivalent mass spring system is given in the complex value. And if you plot this transmission value in the complex axis, like real t and imaginary t as the y-axis like this, and if you plot this transmission coefficient at a certain point, obviously the transmission coefficient should be located on this circle, which means that the absolute value of the transmission equals 1, because we assume the full transmission condition. And the angle of this value, angle phi, should be the phase shift given by the metasurface, this kind of equivalent mass spring system. And obviously, what we want to do is that we'd like to achieve any value of phi, okay? And we'd like to figure out the required value of effective spring and mass coefficient to achieve any desired value of the phase shift, okay? And so this means that we'd like to achieve this value or this value or this value, any value over here. So we can have any desired phase shift by using this kind of effective mass spring system. And very interestingly, we found that, okay, so we'd like to have all of those phase shift as we desired, but the problem is that if you want to have the phase shift which belongs to this region, this red region, then the spring and mass coefficient should become negative value. And okay, so if you want to have the phase shift at the blue region, yeah, that's okay. You should have the positive spring and mass coefficient, which is quite not very challenging. You can easily achieve positive spring and mass coefficient by using the materials or by introducing very specific configurations and all of those things. There is no problem. But if you'd like to have the negative spring coefficient and negative mass coefficient, it's really challenging problem because none of the material existing in the nature has negative density or negative Young's modulus or something like that. But this shows that if you want to have any desired phase shift, including the red region and the blue region, then you should have the unicells which can be treated as the mass spring system having both positive and negative mass and spring coefficient. And that was the main challenge of the elastic metasurface. So to achieve the elastic metasurface, you should have a specific configuration that can have negative or positive spring and mass coefficient. Okay, so how can we achieve that kind of effective parameters? So to achieve negative and positive mass and spring coefficient, we applied this kind of actual structures, okay? This kind of actual structures. Let me explain how we can achieve negative or positive stiffness or mass by using this kind of structure. So here you can see that this structure has two kinds of resonator, one over here and the other resonator pair located at the upside and the lower side. Here the middle resonator provides positive or negative mass effect, while the up and down resonator pair provides negative or positive stiffness effect. So let's see how we can achieve the negative values or something like that. Around the resonance frequency, this configuration shows this kind of deformations. Okay, so as you can see here, Okay, so as you can see here, the middle resonator provides horizontal motion along this direction, while the up and down resonators provide vertical motion along the up and down direction. Okay, let me explain how this kind of motion provides negative or positive parameters. First, let's focus on the middle resonators like this. Okay, so as you can see in this slide, the middle resonators, the mass exhibit horizontal motion, but at resonance frequency, this internal mass provides out of phase motion. That is the nature of the resonance. I think all of you already know about the nature of resonance. So around the resonance frequency, the resonators exhibit out of phase motion compared to the external environment, which means that at the resonance frequency, this the outside part has the right side motion, while the internal mass provides left-sided motion. Okay, so in this case, although the external part provides right-sided motion, which is the plus sign, I think should be, although the external parts provide positive motion, because of the large negative motion of the inside mass, the total inertia becomes negative. Okay, so the total momentum, the total linear momentum becomes negative because the linear momentum is the summation of the linear momentum of all this resonator part. And around the resonance frequency, this internal mass provides large and huge negative motion compared to the external parts. On the other hand, if you measure the velocity is the particle's motion. So the velocity is measured at the outside edge. So which means that the velocity is measured at the sky blue color like this. So which means that the velocity becomes positive around the resonance frequency. Since the linear momentum P is the function of mass and velocity, and the fact that the linear momentum becomes negative value while the velocity becomes positive value indicates that the mass should be negative value around the resonance frequency of this internal resonator. That is the way we can achieve the negative mass by using this kind of structure. So we can, of course, we can adjust the resonance frequency. So at the frequency which does not belong to the resonance frequency, we can achieve the positive mass. And if we tune the internal mass, and if the frequency is very close to its resonance frequency, you can have the negative mass. In the same manner, if we focus on the upsided and downside resonators like this, at the resonance frequency, it provides very large vertical motion like this. And if this mass moves along this direction, then it will provide some squeezing motion like this. It acts as a squeezer, which tries to squeeze the neighboring two elastic materials inside to the mass direction like this. So in this case, even though you exerted force along this direction, okay, even though you exerted force along this direction, usually if you exert this force and then this part usually exhibit this direction, right-sided directional motion, but at the resonance frequency, because of this squeezing motion, then the displacement will become left-sided direction, which means that for the positive force value, you have negative displacement, which corresponds to the negative stiffness value. Okay, so this is how you can achieve the negative stiffness by using the up and down vertical resonator pairs. Of course, as I told you in the previous case, of negative mass case, you can adjust the resonance frequency. So if the actuating frequency does not belong to the resonance frequency, you will have the positive stiffness value as usual in other structures. But if you adjust the resonance frequency so that the actuating frequency is very close to the resonance frequency, you can have the negative stiffness by thanks to the vertical resonators. All of those things can also be derived by using this kind of effective springs having coupling terms like this, but let me just skip the very details. Anyway, as I told you, by adjusting the resonance frequency of each resonators, which is usually done by adjusting the mass value of each resonators, you can actually calculate you can actually achieve any value of desired effective springs and effective mass of this equivalent mass spring system. And obviously you can clearly see that those values can be varied from minus infinite value to infinite value, thanks to this kind of resonating terms. So by using this kind of structures, we can have any value of negative to positive effective densities or stiffness, and by using that idea, we can achieve any value of desired phase shift. So we can achieve the elastic metasurface. We can tailor the wave's propagating direction by introducing very, very thin artificial surface. Okay, so here is the simulation result of our metasurface. You can see that our designed metasurface is inserted here. Of course, the actual geometric parameter for all unit cells are different. But anyway, for all cases, you can see that almost 100% transmission is achieved with the desired phase shift like this. Okay, so you can see the phase shift is slightly linearly varied for each metasurface. So if you combine all of these unit cells to form a single metasurface, obviously what will happen? Of course, the normally instant wave will be refracted along this direction. So we can achieve the wave direction tailoring very easily by using very, very thin metasurface whose thickness is much smaller compared to the wavelength. Okay, so this is the simulation result. As you can see here, thanks to the phase shift provided by each unit cells, if you combine all of those unit cells to form the metasurface, you can see that for the normal instant wave, it will be refracted along the certain direction. And you can actually predict this direction by using the generalized Snell's law, which is very well-known equation in the field of elastic metasurface. Let me just skip this part. And of course, this also works for the obliquely incident case. So if the incident angle becomes 20 degrees, then actually it also works. So the propagating wave, transmitted wave goes different direction thanks to the metasurface. As you can see here, you can figure out how thin the metasurface is. Like as you can see here, is much smaller compared to the wavelength, right? Okay, so that is the idea of the metasurface. So I think this by using these kind of numerical examples, I think you can now understand what is the metasurface and how we can achieve the metasurface or something like that. So as I told you, the metasurface is the artificial thin surface, and by imposing proper phase shift and by imposing proper phase gradient, you can change the wave's propagating direction within very thin surface. Okay, so let's move to the mode conversion case. Let's move to the mode tailoring by using the idea of metasurface. I think all of you already know about the elastic waves mode, but unlike in acoustic waves, elastic wave has its own mode because elastic elasticity is based on the complicated tensor physics. So it has both longitudinal stress-strain tensors, but it has also shear stress-strain tensors, and sometimes they are coupled to provide very complicated wave physics. So even in very simple reflection case, according to the classical elastic waves theory, even in very simple wave reflection case, you can see that even though the longitudinal wave is instant like this, both the longitudinal and shear waves are generated. So in the elastic waves, the wave mode, the coupling between wave mode is inevitable. So it is very important factors. So this is just a plot of the this is the classical elastic waves theory, and you can see that the only way to avoid the generation of shear wave is just at the normal instant case. So as the normal instance case, the shear waves is 0. Shear wave value is 0, and except the normal instant case, the shear wave has non-zero values. So here we'd like to focus on the total mode conversion, which means that at a specific angle like this, as a specific angle, if the longitudinal wave is instant along a specific angle, then we can have only the shear wave like this. So here the longitudinal wave has 0 value while the shear wave has non-zero value. This is the classical elastic waves thing. But anyway, so this kind of thing has been very important factor in elasticity, because in the viewpoint of engineering, in the mechanical engineering, there are a lot of applications which utilize the shear waves in the monitoring or evaluation or crack detection or something like that. But the problem is that usually the generation of shear wave is largely expensive compared to the generation of longitudinal waves. So usually in elastic waves engineering field, they use this kind of certain angles. So they generate the longitudinal wave first because it is much cheaper compared to the generation of shear wave, and they instant that longitudinal wave along this certain instant angles so that they can generate the shear waves only without introducing any very expensive shear wave transducers or wave generators or something like that. The problem is that usually, but this one is only valid for certain angles, so which has a lot of limitations in the viewpoint of engineering. And in the viewpoint of physics, it's also very challenging. So everyone in the elastic wave has desired something like a broadband wave mode convergence, something like this. So if we can have a for example, if we have a metasurface and the longitudinal wave instant along this direction, and if we can have the shear wave along this direction, not both shear and longitudinal wave, but only the shear wave along this direction for broad instant angle, then it will be really a fascinating finding, and it will be a big breakthrough in the field of elastic waves engineering applications. And I think it will be also a very challenging issue in the elastic wave physics. So how can we achieve this kind of total mode conversion for broad angles? So let me just go back to the case. So let's assume that you have the artificial surface. It can be metasurface, but it can be like, for example, here is the aluminum and here is the copper or something like that. And here is the aluminum again. So you introduce any kind of surface here. And according to the elasticity, if you introduce this kind of artificial surface, then even if it is very thin, you will have both longitudinal and shear wave in the transmitted section because of the physics of elasticity. Okay, so because of the physics of elasticity, I mean, in the elasticity, the boundary condition is usually derived in two equations, which means that you should have two waves propagating along this direction. Otherwise, you cannot. The system cannot be solved at all. So this is what happens if you just simply introduce any kind of surface, not tailored surface in here. But as I told you, by using the idea of elastic metasurface, we can tailor, we can change the wave's propagating direction. So by using the idea of metasurface, we can actually, by imposing a proper phase shift, we can change the longitudinal and shear waves propagating direction like this. We can slightly change the shear waves propagating direction like this, and we can slightly change the longitudinal waves propagating direction like this. The sad thing is that we cannot independently change the longitudinal or shear waves propagating direction. All of those things are connected. So we cannot, let's say, we cannot change the longitudinal waves propagating direction only while keeping the shear waves propagating direction. No, that is impossible. But anyway, by using the idea of metasurface, you can change all of those directions within very thin surface. So our idea is, okay, we can change it a little bit more. And what will happen if you change the longitudinal waves propagating direction along this direction, which means that the refracted angle becomes larger than 90 degrees. What will happen? For that case, if you design your metasurface so that the refracted longitudinal waves refraction angle becomes larger than 90 degrees, for that case, the longitudinal wave becomes surface wave. It cannot propagate through the metasurface. It becomes surface wave and it remains at the surface. And the only refracted wave, the only transmitted wave you can achieve is the shear wave only. Okay, so this one is achieved by the idea of metasurface. So it should be broad-banded. It does not hold for, it is not just for the single instant angle only. It is naturally broad-banded, and you can have this kind of total mode conversion for very broad angle until a certain instant angle where both the longitudinal shear wave becomes surface wave. So you can have very broad angled total mode conversion by simply imposing very large refraction angle for longitudinal shear wave, something like that. Okay, so that is the idea of, let me just skip the detailed things. But anyway, by using these kind of theories, you can have, we can figure out that the total mode conversion, which means that the longitudinal wave instant and only the shear wave is transmitted, and that kind of total mode conversion can be achieved at broad instant angle, which was impossible according to the classical elastic wave. But by using the idea of metasurface, you can achieve that kind of thing easily. So by using our previous metasurface, we actually tried that. Okay, so here we redesigned our metasurface to have very large phase shift so that the longitudinal wave becomes surface wave. And here, this is the designed metasurface, and the total mode conversion here is expected to be observed at the angle from minus 20 degrees to 22 degrees, which is quite broad angle. Okay, so based on this metasurface, we did some simulations, and as you can see here, at the instant angle of minus 30 degrees, obviously this angle does not belong to the transmodal, the total mode conversion case. So if the longitudinal wave instant, the longitudinal wave is refracted, and very small value of shear wave is refracted. So this is quite obvious case, but at the angle at the desired angle, at the designed angle, you can see that even though the longitudinal wave instant, there is almost no longitudinal wave transmitted, but there only exists a shear wave transmitted, which means that almost all longitudinal wave is converted to the shear wave thanks to the metasurface. And this simulation is the simulation result for minus 10 degree instant case. And as I told you, this kind of mechanism is not just for a single instant angle. So like 0 instant angle or 20 instant angle, all of those, for all cases, you can achieve the total mode conversion. And this was not done by the simulation only. We also carried out the experiments. And let me just skip the details about the experiments. And yeah, you can see that, okay, so for the degree of -30°, you both have the very high shear wave and very high longitudinal wave, but at the angle of -10, 0, and 20 degrees, you can see there is almost no longitudinal waves like this, okay? And you have only the shear wave as desired. So by using the metasurface, by using very thin metasurface, you can not only tailor the wave's propagating direction, but also if you extend that idea to the mode conversion, you can achieve the mode conversion from longitudinal to shear wave at very broad instant angle, which was impossible in the classical elastic waves theory. And okay, so previous research was quite good, and I expected that I was very happy when I first get that kind of result, but I expected that that kind of idea could be applied in various areas in mechanical applications. But the problem is that in actual applications, none of the system is homogeneous, which means that in almost all applications, various materials are involved. So previously, almost all researchers focused on this kind of case, which means that the metasurface is placed inside the same media, like say medium A, material A, and material A. Okay, so metasurface is installed between the same material. That is the case the previous researchers usually focused on. But if you'd like to extend this idea to the real applications, you should extend this idea to the inhomogeneous case, which means that the metasurface is located between the material A and material B. Okay, so I thought that it would be very easy, but the problem is that okay, so we did the same approach like this. The only change is that now we have medium 1 and medium 2 like this, and we did all of these things. And finally, we figured out that for this case, the only possible transmission is like this one. You can see that the only possible transmission is purely imaginary value, which means that in this case, if the material is different, then the phase shift you can achieve by the idea of metasurface is just 9 or 270 degrees. You can only achieve 2 phase shift if the material is different. Okay, so in the previous case, if the material is same and the metasurface is located between the same material, you can achieve any desired phase shift that you had the freedom. But if the material is different, then for that case, to achieve 100% transmission, you can only achieve the phase shift of 90 degrees or 270 degrees. You cannot achieve any other phase shift, which means that you cannot achieve the wave tailoring, wave refraction, wave propagating directions tailoring is impossible if the material is different. So to overcome this kind of issue, we extended our idea to have the double unit metasurface cases. So here, in this case, as I told you, in this case, if the metasurface is located between 2 different media, then to assure the 100% wave transmission, you can only have the phase shift of 90 degrees. Usually it's 90 degrees. 270 degrees is almost impossible in reality. So you can only achieve the phase shift of 90 degrees if the material is different for the metasurface. So our idea is that, okay, then let's place additional metasurface here. Okay, so here we have the additional metasurface here. Okay, so in this additional metasurface, the material is same. Okay, so this is the additional metasurface. The material is same. The metasurface is installed inside the same material. Okay, so for this case, any kind of desired phase shift is achievable. So our idea is that, okay, we can have if you'd like to have the certain phase shift with this kind of case, first you impose the phase shift or this value, okay? So you'd like to have a certain phase shift, then first you design the metasurface to provide the phase shift, which has a difference of 90 degree compared to the desired phase shift first. And then you put another metasurface which provide the impedance matching, the 100% wave transmission for different media. Of course, this will provide the 90-degree phase shift so that you can have the desired phase shift. So this is our first idea to overcome this kind of issue. Okay, so by that idea, we just made our double unit metasurface like this. And obviously here, the material is quite different. Here, the thickness is 1 millimeter and thickness is 3 millimeter. So although they are in same aluminum plate, if the thickness is different than the impedance, there is the impedance mismatch. So this is same as the different material case. So anyway, we just designed all the metasurfaces by using our idea, and we placed two metasurfaces like this. And of course, since we introduced two metasurfaces layer, there exists separation lengths between these two materials. And if the separation length is too small, if the separation length is too small like this, the metasurface does not work. There exists a resonators coupling between two units. And if the separation is too large, then it doesn't work too. So you should find the proper separation length. But anyway, if you find the proper separation length, you can tailor the wave's propagating direction as desired, like this. And we did also the simulations too, like this, between two different plate. And you can see that in the simulation, you have 1 millimeter plate here and 3 millimeter plate here. And here you introduce some glue-like, very sticky liquid couplant to ensure the bonding between those two plates. And this is the result, and we could have the well-refracted waves. We can have the well-refracted wave tailoring by using the double unit metasurface. Okay, so finally, for the different material case, for the different media case, okay, double unit metasurface worked quite well. Okay, we can introduce two metasurface instead of single metasurface so that we can tailor the waves propagating direction as we desired. But that was not beautiful solution, I think, and you will agree with that. That is not a beautiful solution. What we'd like to do is, okay, we did it with the double metasurfaces, but can we do that with a single metasurface, just a single metasurface, so that the size could be much more thinner compared to the previous case? And we did a lot of researches, and recently we published a paper that it is possible to have a single unit metasurface, single layer metasurface, even if the material is different for the metasurface case. So the idea is the asymmetry case. So previously, so this is what we did. The idea was the asymmetry. So let me just explain that briefly. So previously, we used this kind of mass spring system. Here, the spring coefficient, the same spring is installed at the left side and right side of the mass. And if you calculate the transmission coefficient and reflection coefficient like this, you can have this kind of result. And to ensure the zero reflection, which means that to ensure the 100% transmission, you should have this kind of conditions, and if you put this kind of conditions to the transmission coefficient, you will have the purely imaginary transmission, which means that if you use the same springs here and here, so if the mass is connected with the same springs, then you can only have the 90 or 270 degree phase shift only, which is the issue I explained in the previous slide. But we found that if the mass spring system becomes a symmetry, now we have the different spring connecting the mass. We have the alpha at the left side of the mass, and we have beta at the right side of the mass. And if you have this kind of asymmetry, then the total equation becomes quite different. For this case, the equation becomes like this, and to ensure the zero reflection, the condition becomes quite different. And if you have this kind of case, the transmission coefficient becomes like this. You can see that for the asymmetry case, the transmission coefficient has not only the imaginary value, but also the real value, which means that you can now have a freedom to have any desired phase shift because the transmission is not purely imaginary value anymore. Now it is a complex value having both real and imaginary value, so you can have any desired phase shift if you have this kind of asymmetric mass spring system, okay? So by using this idea, we actually changed our previous configuration. So obviously you can see that unit cell becomes a symmetry, which means that the parameter here and here is different from the parameter here and here. So this configuration becomes asymmetry to ensure the asymmetry in this case. And here we designed this metasurface so that we found that with the asymmetry, we can achieve both the full transmission and any desired phase shift by using a single layer metasurface. And then we also found that, okay, we can have this kind of very nice reflection direction tailoring by using a single layered metasurface only. And also since now it's possible to tailor the waves propagating direction between two different media, now it is also possible to achieve the total mode conversion for broad angle between two different media, as I explained previously. So this is the result. So this is our newly designed metasurface, and you can see that the longitudinal wave propagating along this direction, and there is no longitudinal wave transmitted, and there is only shear wave transmitted along this direction, which means that all longitudinal wave is converted to the shear wave like this. And this one is also not just for a single instant angle. You can see that, okay, for this angle is okay. For the normal instant case, it also works. And for other instant angles, it also works. So the total mode conversion is still achievable between two different materials if we can adopt the idea of asymmetry. So by this presentation, I just explained about the main idea of metasurface. So the metasurface is the research that designed the unit cells to make a very thin surface, but it can change the waves propagating direction along any desired directions. And I showed the idea of total mode conversion. So by using the idea of wave direction tailoring, we can also achieve the total mode conversion from longitudinal to shear wave at broad instant angle, which was impossible according to the classical elastic waves theory. And also, I just mentioned about the recent challenges in elastic metasurface, that the metasurface is installed between two different media. You should have additional specific idea of asymmetry. Otherwise, you cannot have the wave propagating direction change. Okay, so I think my time is done, and thanks for listening my presentation. And And thank you for listening to my presentation. And if there's any questions, I will be glad to answer about that. Thank you very much.
Okay, thank you. Thank you for your very interesting presentation. My name is Yoo Hwan Oh. Can you hear me?
Yeah, I can hear you, Professor.
Yeah. Okay. I have a question about the first part of your presentation. It's about tuning of phase shift with complete transmission.
You're right. Yeah.
Yeah. I have a question. Is it possible to design unit cell to tune the both the phase shift and the transmission coefficient arbitrarily?
Yeah,
Is possible?
Yeah, that's very nice question. Yeah, my answer is yeah. So in this presentation, I show the case for 100% transmission only, but it is also possible to make the unit cells, for example, having 0 transmission or 50% transmission with the desired phase shift too. Yeah, it is possible. Yeah.
Okay, it's good. Very good. It's a very smart idea to design the unit.
Yeah. So
another question. Is about a double metasurface between two dissimilar materials.
Yeah, right.
I noticed that you said you have a separation. Between the two metasurface.
Yeah.
And we must choose the value of separation to get a perfect transmission.
Yeah, right.
So I want to know why. Is it because some kind of resonance or?
Yeah. So yeah, thanks for a very nice question, and I'm sorry that I missed that part when I explained this slide. Okay, so you can see that. Okay, so here you have the two metasurfaces here, and you have the separation length between those two metasurfaces. If the separation length is very small, which means that if two metasurfaces is very close to each other, then the metasurface has a resonator as its unit cells. And if the two metasurfaces is very close to each other, the resonators at this surface is coupled with the resonators at this surface. Okay, so that is the first reason that the separation length, if the separation length is too small, it doesn't work. And if the separation length becomes too large, for that case, the waves transmitted through the first layer is fully developed, so that the wave wave direction is tilted. So here it is plotted in the white arrow here. So as you can see here, if the separation length is too large, then the normal instant wave is after it penetrates through the first layer, it is fully developed and it becomes obliquely instant wave along the second metasurface case. And since the second metasurface is not designed for the obliquely instant case, it is designed for the normal instant case only. So because of that, in this case, the second metasurface performance becomes very low, so that it has very low performance. So if the separation length is very large, then the transmitted waves are fully developed. So we should avoid that kind of large separation length. So that is why we need a proper value of the separation length. Yeah.
Okay, and then how can we find the optimal value
Ah.
of the separation length?
Yeah, to be honest, we tried various separation
Okay.
lengths and we just figure out the best one. So currently we don't have any strategy to define which one would be the best separation length, honestly. Yeah. But because of that issue, we just carried out our researches to not use the double layered metasurface or something like that. Yeah.
Okay, thank you. Thank you very much.
Yeah, thank you very much for the very nice questions. And I'm sorry that I missed some important part in my presentation. Yeah.
Okay, thanks. And also, Professor Oh, we have some questions from WeChat from Wolf.
Oh.
So I just transfer to the chat part. Maybe you can see.
Ah.
So the first question is, thanks for sharing your excellent work.
Yeah.
Just wondering, can metasurface be used to control inelastic wave propagation, considering material damages?
I'm not sure what's the actual meaning of inelastic wave propagation because I just focus on the linear elastic wave, which is defined as P and S waves inside the case. Does it mean acoustic wave or some related to other physics, or does it mean some nonlinear waves or something like that? If that question means the acoustic waves or something like that, yeah, the answer would be obviously yes. There's a lot of researches for acoustic metasurface, and if that question, I think that question is related to the nonlinear wave. I mean, inelastic or plastic or something like that. If the question is related to the linear elastic wave, and then my answer is currently I didn't try that, and obviously I think that my metasurface itself would not work for the linear regime. It will only work for very small amplitude case only. But I can say that there are other papers, not in my group, but in other groups which are focusing on the linear elastic metasurfaces. And if you can use their idea, I think it would be possible to deal with those kind of nonlinear elastic waves. But just one thing that even for those nonlinear elastic metasurface group, they only consider very small nonlinearities. So if you are focusing on very large nonlinearities, that my answer would be negative. I'm sorry for that.
Okay, thanks. Actually, inelastic is not elastic, so
Yeah.
it's rebound. And also the second question is have 3 points.
Yeah.
So first is with regard to the transmode metasurface.
Yeah.
It involves 2 kinds of wave, P and S.
Yeah.
So the design phase shift for P and waves is determined by the type of incident wave.
Yeah,
Is that
right. So in our case, we only considered the mode conversion from P to S wave, which means that we assumed that the incident wave is only the P wave. But it is also possible to design the metasurface based on the shear wave instant case. And we recently published a paper which works for both P and S waves, both P and S wave instant case. So yeah. So the answer would be, yeah, you're correct. Currently, we assumed that the instant wave is P wave type, but it is also possible to design the metasurface based on the S wave instance types. And thanks very much for a very nice question. Yeah.
Okay. The second point is talk about some experiments. He's wondering some details on how to excite a longitudinal wave in a thin plate.
Okay, thank you very much. Yeah, so usually when we think about the wave experiments, we usually think about using piezoelectric transducers. But the piezoelectric transducer is good for actuating flexural waves, but not very good for actuating longitudinal wave. And here in our experiment, we did not use the piezoelectric transducer. We used the transducer called EMET sensor, EMET transducer, electromagnetic acoustic transducer, which is already commercialized transducers. So instead of using piezoelectric material in this kind of EMET sensors, they utilize the Lorentz force to actuate the longitudinal wave. So here you can see that this is the schematic of the EMET sensors. Oh, I'm sorry. Yeah. Yeah, this is the schematics of the EMS sensor. So here, this EMS sensor consists of the permanent magnet and coil. So permanent magnet provides a magnetic field inside the aluminum plate, and within that permanent magnet, the actuating coil provides dynamic magnetic force, which makes eddy current inside the aluminum. And because the eddy current is generated inside the aluminum plate having very large magnetic field due to the permanent magnet, then that kind of there is the electric force generated by the Lorentz force, and that Lorentz force generates the longitudinal wave. So we use this kind of EMET sensors and transducer. This one is actually commercialized one. This one is not our own techniques or some secrets or something like that. You can easily buy that kind of transducers in other companies. Actually, I know some Chinese companies which make this kind of transducers too. And even in our experiments, we use the transducer we bought in Chinese companies. So we used that kind of commercialized EMET transducer to carry out this kind of experiments. And just one more advantage of using the EMET transducer is that it can not only depends on the configuration, it can be tuned to generate or measure longitudinal wave, but it can be tuned to generate or measure the shear waves too. So this is the really good point of the EMET transducers. Yeah.
Okay. Yes, and also the third point is also about this incidence of longitudinal wave. Is it possible to use the piezoelectric film to excitation? Used for the
excitation of the fluctuating waving. Yeah, right.
Wave.
Yeah, right. Yeah, the question is very brilliant and very critical question, because usually if you use the piezoelectric transducer, it generates a fluctuating wave usually. So it is really hard to use the piezoelectric transducer to generate longitudinal waves. And actually, we did some experiments using the piezoelectric transducer for the longitudinal wave, and for that case, we installed two piezoelectric transducer at the upside and bottom side of the plate, and we generated those transducers like this. So by this way, the fluctuating wave is totally eliminated, and you can actuate the purely longitudinal wave if you install two piezoelectric transducer at the upside and lower side of the plate. But the problem is that, okay, for that case, you can actually generate the purely longitudinal wave only by using two piezoelectric transducer pairs, but the source is omnidirectional. It doesn't have any direction. So if you see the plate here and piezoelectric transducer is located here and here, for example, in that case, the wave will spread like this. It does not have any direction, which is usually not very good at this kind of metasurface experiment or something like that, which requires some directional wave source. And if you want to have some directional wave source, again, I'd like to suggest to use the EMET sensor or something like that. I'm not the one who's selling the EMET sensors, but anyway, the EMET sensor is a directional source. It has a certain direction, so it would be really good if you are looking for some directional longitudinal source. But the disadvantage of using the EMS sensor is that its output is quite not very strong compared to the piezoelectric transducer. So if you need very strong source, then I'd like to suggest to use two piezoelectric transducers at the top and bottom surface of the plate. And if you want to use the directional source, then I'd like to suggest to use the EMET transducer and sacrificing the amplitude of the generated wave. Yeah.
Okay. Yeah. Thanks for this question. Actually, when we're talking about this flexure wave, I'm also wondering, maybe I missed some part of your presentation. So, did you consider or already consider the wave control of flexure waves? I mean, maybe you can transfer flexure waves to longitudinal to shear. Did you think
that's very
possible?
Yeah, that's very good idea. Currently, we are just focusing on the longitudinal or shear waves only because here I'm thinking about the non-destructive evaluation as the possible applications, and usually in imaging, like elastic wave imaging, ultrasonic imaging, they use the longitudinal or shear wave, not the flexure wave in usual. But yeah, that's very nice comment, because very recently I started some researches for the flexure waves metasurfaces too. And yeah, for now, this kind of research is just for the longitudinal and shear waves only. And maybe after 5 years or something like that, if you give me another chance, I can show some of the results. Yeah.
Okay. Maybe I think it's maybe a bit difficult because of the governing equation is a bit complex.
Yeah, exactly.
Compared to the longitudinal and shear waves.
Yeah, exactly. Yeah, here seems like here we have one more question.
Yeah, we have one more question. Is except for the introduced way to realize mode conversion, are there any possibilities to realize mode conversion without any energy loss of the surface wave or angle limitation?
Oh, thanks very much. And it's really important question. This is really important question that I'm really thinking about. Yeah. So, okay, there are various ways to achieve mode conversion, and yeah, to be honest, it really depends on what kind of mode conversion you want to achieve. So, in my research, my main goal is to achieve mode conversion for broad instant angle, and for that case, there could be some other techniques, but for now, I just figured out that kind of thing would be the main factor, and there could be some other result, some other way, but currently we are focusing on that topics. But for now, I can say that if you are looking for broad instant angle total mode conversion, then I think this would be perhaps the only way, and there could be other approaches, but as far as I know, this would be the only way. But if you are focusing on other kinds of mode convergence, for example, if you are considering about the case where the instant angle is fixed and then you want to achieve the total mode conversion, then there are various ways to achieve that kind of total mode conversion. So you can refer to the transmodal fabric parallel resonance, which was published in PRL in the year of 2018 or 17 or something like that. Yeah, you can also check that kind of things too. And also there are other very nice researches focusing on meta gratings or metasurfaces just for a single instant angle, but providing very, very nice and very, very great performance of the total mode conversion. So if you are focusing on just for the total mode conversion, and usually in almost all applications, the instant angle is usually fixed. And if you are considering about that kind of case, you can find a lot of other approaches which provides much, much better performance compared to my case. Okay, so in my presentation, my goal is to achieve the broadband total mode conversion. But that is not necessary, to be honest. So if you're focusing on other kinds of total mode conversion, there would be so many other researches, and and I've read a lot of papers about that kind of topics. I think you can also easily find a lot of ideas. And yeah, to be honest, I've read a lot of very nice papers from Chinese group about that topics. Maybe you can find that much easier than me. Yeah. Because usually especially for the elastic ultrasonic wave applications, I think that the average level is much higher in China compared to other countries, like in industrial part or in the physical part or something like that. So yeah, there's very nice researchers in China, so you can easily contact those groups. Yeah.
Okay, thanks. So any other questions? Okay, so if no, maybe it's the end of this lectures. So thanks so much, Dr. Oh, for your very excellent presentations and also for the nice answers to all the questions.
Yeah.
And yeah, I do hope that maybe this year, next year, if things are fine, and you can visit China, visit Tianjin University. So then
that would be really great, because as I told you, whenever I've visited China just one time previously, and when I visited there, I was really shocked that every researchers were, especially for elastic waves, is really great. I really enjoyed that experience, and if I could have one more chance, I would be glad and honored to be with you. And thanks for all of the audience, and thanks for all of you for spending your time with me. Yeah, thank you very much.
Okay. Thanks, and also you are welcome. Actually, if you have if you have time, actually, let me know, and then we can invite you to visit us. Yeah. Okay. So thanks, and thanks for all the attendees. And now is the end of this lectures. So bye bye, and see you.
Thank you very much.
All the others next time. Yeah, bye bye.